now we're going to look at some other examples of conservation of energy problems. I'm calling this dual credit mainly because these are situations that again could arise on the AP exam, but again, everybody should watch this just because of the help that you'll get. All right, so here's an example. We got an initial height that we don't know. Oh, we do know. Sorry, it's 3 meters. We want to find the velocity when it has fallen 1 meter above the ground. So we want to get to about this point, right? 1 meter. And you can see from the diagram, at the top we have all potential. At the bottom we have all kinetic. That would make the math pretty easy going from top to bottom. But somewhere in the middle, that's where we got to think about how the energy is being transferred. We look here, smack dab in the middle, they're equal to each other. So 1.5 feet down, or 1.5 meters down, that's what we'd see. So what we want to look at is that we're going to assume that this is going to be all conservative forces, just gravity acting on the object. So we have kinetic energy initial plus potential energy initial equal to kinetic energy final plus potential energy final. And we're going to start looking at this object. Now initially, up here, we have all potential. So initially there's no kinetic energy. Okay, so we're going to get rid of that. And all we have at the beginning is potential. In the middle, we have both potential and kinetic. So we got to keep them both there. So now let's just start writing out what we know. Okay, we don't know the mass, so we got mass, which we don't know. We know G is 9.8, and we know our height is 3 meters. So there's our potential. For kinetic energy, 1/2, we don't know the mass, velocity squared, okay, we don't know that, so we don't know a lot there. But for here, we don't know mass, but we know G, and we know our height is going to be at 1 meter. Okay, so first thing I want to do is look. I got M in each of these groups, in each of these situations. So if I divide both sides by M, which I can do algebraically, all right. So divide by M, divide by M, divide by M. Masses all cancel. Now my math is this. So I got 29.4. I got 1/2 v squared plus 9.8. Now this is kind of magical here because now look what I can do. Now I can solve for v. I can subtract 9.8 over. All right, and I get 19.6. 1/2 v squared. I multiply by 2 to both sides, and I get 39.2 v squared. Take the square root of both sides, and my velocity at 1 meter is 6.3 meters per second. So algebraically, I don't need to know mass to find that final velocity. That makes your math a heck of a lot easier. Remember that idea when we're doing energy problems. Okay, so same idea. We got a roller coaster car, and we assume the height to be 40 meters when the roller coaster car starts from rest. We want to find the speed at the bottom of the hill, so we want to find the speed here. And then we want to find this at what height will it be half its speed. So at what height will speed be half? And we want to take, and this is important, the bottom of the hill to be 0. Why do we do that? To keep our numbers on the positive. And you'll see as we do the math why that's important. So again, we're going to assume that there's no friction. We're going to keep everything conservative forces. So just gravity's acting on our object. So we got potential and kinetic energy initial, potential and kinetic energy final. All right, no friction yet. So we're going to look at this, and again, at the top, we're starting from rest. We can eliminate kinetic energy. At the bottom of the hill, right? At the bottom of the hill, we see that we'll have no potential energy because we're at 0 position. So now we just got potential energy initial equals kinetic energy final. Boom, piece of cake, right? So we don't know the mass, 9.8. our height is 40, and that's going to equal 1/2 mv squared. Now remember, masses will cancel here, so now we got 1/2 v squared equals 9.8 times 40. Math comes out really easy, okay? And again, I'm not going to go through the whole math process with you. I'm going to give you an answer. Please check my math. If you see an issue, let me know. But when we solve this, our velocity at that point is going to be 28 meters per second, okay? So I'm at 28 meters per second at the bottom of the hill. At what height will it have half this speed? Okay, half this speed. So we want to look at this situation the same way, okay? And what we don't know the height. It'll have half this speed. We know half the speed is going to be 14. So what I would do is I would set up the same problem. Kinetic energy, potential energy equals potential energy plus kinetic energy. And just see what I can do with this. Now, at the very bottom, right, we know what the speed is. So I'm going to say at the very bottom, I have no potential energy, but I do have kinetic. All right? And I'm going to say I have 1/2 m 28 squared. We go halfway up, which half its speed, but we don't know what that height is. We do have potential energy at the final, and it's going to be m, right, times 9.8 times our height, which we don't know. So we don't know m or h. And then we know half the speed. Half of 28 is 14. And we go 14 squared. Again, our masses cancel out. When you look at the math, only unknowns h. We solve for h in algebra. And again, I'll leave the math to you. When you round, should get 30 meters. And there's no way to do this, and if you find a better way, please go ahead and do it that way. But there, you could work opposite and start from up top and go halfway down. But anyway, that's our answers. And again, mass, not important. All right, so this is very similar to what we saw on the first video, is that we have two slides of the pole shaped differently but start at the same height. Two riders start from rest at the same or different slides. Which rider, Paul or Corrine, is traveling faster at the bottom? Which rider makes it to the bottom first? Ignore friction and assume both sides have the same path length. So if we ignore friction, the same path length really not important. If friction was included, then the path length definitely would mean something because it would be a non-conservative force. But since it's all conservative forces here, just gravity acting on us, without having to do any math at all, we know that if they start the same height, they're going to have the same speed at the bottom. Which rider makes it to the bottom first? They'll make it at the same time. That's where path length would be important. We talk about time, but not speed. Obviously, if they travel the same speed, whichever one had the longest path length would take the longest to get there. Hopefully that makes sense. All right, now let's talk about elastic potential energy and how we can relate this. A dart of mass 0.1 kilograms is pressed against the spring of a toy dart gun. The spring with a spring stiffness constant of 250 and no mass is compressed 6 centimeters and released. The dart detaches from the spring when the spring reaches its natural length. What speed does the dart acquire? So now we're looking at all potential energy. So we got, let's write down our start here. Potential energy spring plus kinetic energy initial equals potential energy spring final. Sorry, put initial there. Plus kinetic energy final. And so, first question is, at the start, the dart's obviously not moving. No kinetic energy. At the end, it says the spring reaches its natural length. So there's no spring energy at the end. So really, we're talking about initial spring being converted to kinetic final. And so our spring is 1/2 K, which is 250, times the distance squared. Now remember, we want that in meters, so we got 6 centimeters. We want 0.06 meters. We want that squared. Is equal to 1/2. And we have to have the mass here. Okay, if we don't have the mass here, that's a problem to try to find that velocity. But here's our problem set up again. We have everything but the velocity squared, or the velocity. We just solve for velocity. and we get 3 meters per second when we do the math again. Always check my math. Okay, so here we get another situation of a ball dropping on top of a spring. It falls 55 centimeters, strikes the spring compresses 15 centimeters. We want to find the constant of the spring, and we want to assume there's no mass of the spring, and we want to ignore air resistance. Again, air resistance would be one of those non-conservative forces, so we don't have to worry about non-conservative forces. We want to measure all distances from where the spring is here, so we want to make that 0. Okay. Now to do this, we got to break this apart into two situations. We want to talk about before the spring hits and after the spring hits. So before the spring is hit, we got potential energy, kinetic energy, potential energy, kinetic energy. Okay? At the very top, obviously we're not moving. And at the very bottom, okay, we're going to say that we don't have kinetic, that the ball is going, that the energy, or no potential at the bottom because that point's 0, right? And we have kinetic. So we got potential energy initial, kinetic energy final. Because our height's 0 at the point where it hits the spring, obviously we have no potential. So we go MGH, 2.6 times mass, or I'm sorry, G is 9.8. And our height 55 centimeters, that's 0.55. And that's going to equal 1/2 times our mass, which is 2.6, and we'll find that velocity. Okay, so we're going to find the velocity of the ball when it gets to the spring, which is 3.28 meters per second. Now we're going to take that velocity and talk about the energy that happens here. So from the point where the spring's hit to where it compresses, all right, here's what happens. We see the spring slow down the ball to a stop. So what we have is we have potential energy of the spring plus the kinetic energy. That's going to equal the potential energy of the spring plus kinetic energy. Now, since the ball comes to a stop, we have no final kinetic energy. And since the spring hasn't started to be compressed, we have no initial spring compression, so no initial spring energy. So all we got is kinetic energy initial and spring. So what we're looking for, solving for, is K. So we know the speed when it hits. It's 1/2, and it's 2.6 kilograms. And in our speed, we solve for 3.28 squared. And that's going to equal our spring, 1/2. K we don't know, but the compression is 15 centimeters. Again, make sure you convert it to meters, 0.15, and we square it. In the end, we're going to solve for K. It was kind of a jumbled mess here, but as you're taking your notes, give yourself some room. K, when we do the math, in the end should equal 1590 newtons per meters. I will finish the last problem on another video. I'm going to run out of time for this one, so please look at that one.